we're talking about Laplace equation, right? This is this equation, delta u equals 0. U is a function given somewhere in Rn. X is a vector that has components. And in addition to Laplace equation, we will be talking a little bit later about its inhomogeneous version, Poisson's equation. And let me remind you the definition that C2 function, which is a function that has a continuous derivative of the second up to the second order, satisfying Laplace equation, it's called a harmonic function. And in Cartesian coordinates, Laplace's operator can be written as the sum of second derivatives with respect to each component. And it is obviously a linear equation and second order equation, it's second order PDE. And for linear equation, one of the strategy could be is just find a simple explicit solution and assemble out of simple explicit solutions more complicated solutions. And if we keep in mind this strategy, we can note that Laplacian is invariant with respect to a group of Euclidean motions that includes rotations and translations, and we can use this property to construct property rotation invariance with respect to rotations. We can use this property to construct a radial solution, and that would be a simple solution because it will help us to transform our PDE to an ODE. And the way we're doing this, we just replace our vector x with its magnitude, which we call r, and this is obviously the square root of a sum of squares of components. And let's assume that x is a non-zero vector. And now let's do the transformation of derivatives. And we can, one of the ways is to write down the first differential in the old variables and in the new variables and use the property invariance of the first differential. And so here we will have du dx1 dx1, du dx2 dx2, and so on. And it will be equal du dr dr, r will be the only variable. And what is r? R is written here. So if we compute the differential of r, that would be derivative with respect to x1 dx1 plus derivative with respect to x2 dx2 and so on. And then we differentiate here with respect to, say, x1. It will be 1/2 square root in the bottom and derivative of inside 2x1, 2 and 2 will be cancelled, so we will have x1 over r dx1. And we will get similar expression for every variable, x, and the last will be xn over r dxn. And then we equate coefficients of dxi. So for dx1 we will get here du dx1, and here we'll get x1 over r. So for every variable components of vector x, xi will get d dxi equals xi over r d dr. And to write down the Laplacian in this new coordinate, we need to replace the second derivative as well. So to compute second derivative, we need to differentiate du dxi with respect to xi again, and then we know that du dxi will be x using this formula xi over r du dr, and then we use the product rule to differentiate. We differentiate the first factor here, du dr, plus the second, and then we will use the quotient rule here to write down the derivative. And here we will just replace d dxi with xi over r d dr. And then we'll just make some obvious simplification, having our expression for second derivative with respect to xi in this form. And Laplacian is the sum of second derivatives, so then we will compute the sum, we will put this first term here, we will combine it as a single fraction, and then we will compute a sum of everything, so it will be a sum, and then for the first term here we can pull out 1 over r cubed and du dr, and that would be just sum of this expression, and plus du dr squared can be pulled out, and sum of expression like this. And when we perform the summation, we will get n times r2, and this will summation of all xi squared will give us r squared, and finally we will end up with this expression. So, and then our Laplacian will be transformed into this second order ODE. So here I just replace u of x. Now instead of x we have vector x, we have just single variable r, and I just change the name of our function, calling it v of r, and for v of r we have this equation. Again, deriving this equation, we assume that we are not at the origin. R is not equal to 0. Okay, so we been looking for a radial solution. So we got our ODE, which I have copied here, and then if v prime is not 0, then we can divide it by v prime, and then we can notice that in the left hand side we have derivative of logarithm of derivative of function v. We can derive it like this, and then we can integrate both parts, and with respect to our variable r, and then for v prime we will get this equation, and then we will have two different cases when in the bottom we have expression of 1 over r or not, and 1 over r will correspond to the value of n equals 2. So if n equals 2, v prime would be some constant c over r, and then v would be this logarithmic function, and if n equals 3 or greater than 3, then integral will give us some constant over r to the power n minus 2 plus another constant. Right? So we got our radial solution v, and the assumption was that r is not equal 0. And now I just want to show that if we take this solution, for instance, if we take the solution that we got, a radial solution, let's ignore the constant, and since we are dealing with a linear operator, and the claim is that if we compute Laplacian of this function, that will not be equal 0 throughout the space. And we can guess what the cause is. The cause is that 0.0, so we can, to show that this is not equal to 0, we can integrate this taking some subregion that includes 0. And so to compute Laplacian, let's first compute the gradient, and that would be gradient of this expression if I just replace r with x1 squared, square root of x1 squared plus x2 squared plus xn squared, and then we will just compute derivative with respect to each xi of this expression, and we will get this. Obviously, if we have here to the power n minus 2 over 2, then it will be this number, and here we have to just power will be 1 less, derivative of inside, and finally we will get the gradient of this function is 2 minus n, and each component of the vector will be xi over rn. And now let's call this vector f. And to simplify the computations, let's just consider a specific case. Let's assume that n equals 3 and omega is a unit ball. And let's use the divergence theorem, or this specific case, special case of Stokes theorem. And in this case, instead of computing integral over the subregion over the ball, we will just take integral over the sphere, over the boundary, and that would be normal component of our vector f, which is this one. And so in this specific case, 2 minus n, if we take n equals 3, will become -1, and then this is our vector f is here. Normal to the ball would be just outward normal x1, x2, x3 divided by the magnitude of the vector. And when we compute the dot product, multiply these two, we'll get r squared or over r to the 4th. But we remember that we're computing this on the unit sphere, so it will be 1, and finally we will get -1 times integral just over the surface of the sphere, so that will give us area of the spherical surface, and that area would be equals 4 pi, and this is definitely not equal to 0. So how we can generalize this or compute this in n-dimensional case? So then here we will have some n form, here we'll have the corresponding n-1 form, and then this -1 came from 2 minus n, so we'll get 2 minus n, and times will be area of the unit sphere in Rn. So we can, so what we've been doing, we've been computing integral of our radial solution that we got, and this integral, if we use unit ball, will be equal to that. So then if we normalize our function, if we divide by this constant, we will get something that's a function that will give us, whose integral over the sphere would be 1 if we just divide it. Let's just keep that in mind. Let's also make one more comment. So here, when we're computing this, we said that we take unit ball, but Actually, our solution has a very amazing property. What if instead of a unit ball, we were taking just any ball that centered at the origin? Then what would be different? We will do the same computations here, and when we arrived at this part, right, suppose we have here a sphere of radius r, right, say big R. Then on the sphere here we would have this would be cancelled, so here we will have 1 over r squared, so then we will have -1 as we had in a three-dimensional case, and here we will have 1 over r squared, and then it will be area of our sphere, which is 4 pi r squared, and that would be cancelled, and the answer still would be -4 pi. And this is the property that I should have mentioned. So the flux through the sphere, it doesn't depend actually on the radius of that sphere. So our radial solution normalized in such a way that the integral just over the sphere centered at the origin equals 1 looks like this. So here I wrote this for n greater or equal than 3, it will be 1 over 2 minus n, and omega n is the surface area of the unit sphere in the Rn, and here would be just magnitude of our vector x to the power n minus 2. This is the solution we were talking about, and in the two-dimensional case all of the computations are pretty similar, and here the omega in this case would be just a circle, so we will have just the circumference, which is 2 pi r, and since we mentioned that r is not important, it will be cancelled anyway, so it's 2 pi. So that is why we can write that omega 2 here, it would be just 2 pi. So that would be our solution, radial solution in two-dimensional case, and in three-dimensional case we computed omega 3 is 4 pi. For any other dimensions we can write this formula. The formula for the surface area of the unit sphere is 2 pi to the power n over 2 divided by gamma of n over 2. This is gamma is a gamma function. It can be defined using this formula, but for specifically we will need just integer positives n, and the formulas we will need is just gamma at n equals just n minus 1 factorial, and gamma at 1/2 plus n equals 2n factorial over 4 to the n factorial square root of p. And we can check, for instance, we can use this general formula to get 2 pi. Then in this case n equals 2, so 2 over 2 would be 1. We have gamma at 1. Gamma at 1 would be just 0 factorial, which is 1. And here we will have 2. 2 over 2 is 1. So we will actually get 2 pi. So that's what we have. And for, say, three-dimensional space, we can check this formula. In this case, n equals 3, so we have to compute gamma at 3/2. So gamma at 3/2, if I want to use this formula, so in this formula, just maybe it's a little bit confusing, but this n would be equal to 1. So then we will get gamma at 3/2, and if this n equal to 1, then we'll have 2 factorial, which is 2. Here we have 4, so it will be 1/2, and n is 1, so we just get 1/2 square root of pi. And then we have to go here and take 2 pi to the 3/2 divided by 1/2 square root of pi, and 1/2 in the denominator will give us 4, and we will get just pi to the first degree. So everything will be satisfied. So we have established that this solution, which by the way is called the fundamental solution for Laplacian, satisfies Laplace equation everywhere except the origin. And what would be the right equation to write down for this solution so it satisfies this equation everywhere throughout the space? And that would be this equation. So we will write delta u, Laplacian u, equals delta of x, where delta, this small delta here, is Dirac's delta function. And we can comment that if we add here any harmonic function, so function that satisfies just Laplace equation with 0 on the right hand side, it still will satisfy this equation. So the fundamental solution is not uniquely defined. It defines up to the regular harmonic function.